The control room went silent first, then came the gasp. A star in a quiet corner of a familiar galaxy swelled like a heartbeat seen through fog, brightening in a way that made instruments squint and astronomers sit up straight. It had blown itself apart already. Everyone agreed on that. A dramatic death written in light. And yet, here it was again, rising like a lighthouse unburied from the sea. This should be impossible. When stars die, they do not send postcards. When they explode, they do not rehearse. But something hidden was waiting in the dark, and it had just pressed the trigger again. What you are about to see will change how you think about the universe. We were taught a single story. A star spends its long life burning, grows old, and collapses into a last spectacular blaze. Curtain, fade. Cold embers. But there are stars that refuse that script. They detonate, recover, and detonate again, throwing their own shrapnel into space like a heartbeat that hurts. Imagine a volcano whose crater reforms by morning, only to roar by evening. Imagine a forest that regrows in a night of wind, only to ignite at dawn. These repeaters live on the edge where gravity strangles and fuel begs for fire, and every outburst is a renegotiation with fate. The first photographs are always deceptive, grainy swells of light in a field of patient stars. But the pattern is unmistakable. A pinprick blooms to a wound recedes to a scar. Then, without ceremony, the scar opens. Telescopes built to surveil the ordinary rhythm of the sky suddenly find themselves chasing a returning storm. Across months or years, brightness rises and falls like the sea trying to climb the moon. Each flare writes a new chapter onto the same page, and the page keeps taking ink. It is tempting to call this magic. It is not. It is fuel, gravity, and a resettable trigger. Picture a dead core the size of a city, crushed to a weight that would fold mountains as if they were paper. Picture a neighbor star leaking its skin across a gravitational bridge, drop by drop, like rain fed into a locked furnace. That furnace waits. It piles a thin, volatile film on its surface, a film that wants to burn but cannot, until pressure tightens like a hand on a match. Then the flame runs, sudden and unstoppable, across that skin. The star flashes. The sky takes note. Most of the core survives, scorched but intact, and the rain begins again. The cycle resets, the countdown restarts, and somewhere an astronomer opens a fresh notebook with shaking hands. Not all repeaters share the same anatomy. Some are compact embers stealing breath from companions, their flares like camera flashes in a crowded room. Others are giant, unstable titans, so luminous that their own light becomes a wind, peeling their outer layers with a brilliance that can mimic a true death. You might call them zombies if you like the taste of that word. Stars that keep standing up after being cut down, yet even that metaphor feels small. What they are doing is rewriting the laws of the cosmos we thought were settled, not erasing the rules, but showing us the clauses we missed, the side doors, the loopholes carved by heat and crushed by gravity until they shine. We read their light as if it were a confession. The rise tells us how quickly the fuse burned. The color tells us the temperature of the ash. The drop tells us how the debris cooled, how it collided with old shells shed in earlier tempests. Sometimes the returning flare is brighter because it runs into its own history. New blast meets old breath, and the collision turns motion into light. Imagine throwing a stone into a pond and watching ripples strike a hidden ring of ice. The splash blooms twice, louder the second time, not because the stone is heavier, but because the pond was already waiting to fight back. You might ask, why should this matter to us, who live in the quiet space between beats? Because each outburst is not just spectacle. It is decision. Every eruption either strips the star, bleeding mass into space, or tightens the noose of gravity by letting the core fatten on what remains. Each detonation nudges fate. One path is a slow, endless shedding, 1,000 storms that never settle. Another path is a tightening spiral toward a catastrophic light that will tear the star to atoms and leave a beacon that can be seen across the cosmic sea. These are not fireworks. These are votes cast in a fierce election where the candidate is oblivion. Listen closely to the language of watchers who spend their nights following whispers of brightness across motorized domes. They talk about clocks. Clocks wound by accretion, by wind, by pressure in layers thinner than paper, yet heavier than worlds. Clocks that tick in years or decades, that skip beats, that speed up as the core grows denser, as if time itself were a staircase narrowing to a point. When the second hand hits the unseen mark, a fuse catches, and the sky learns a new word for heat. Then the hand keeps moving. What you are watching is a promise that the universe has a memory. A star throws off a shell. It does not vanish. It hangs there, a ghostly ring awaiting the next blow. Light from the new blast catches that ring and makes it sing in radio and X-ray, a choir of frequencies telling us about particles whipped to near light speed, about dust grains forged in chaos and set adrift to seed future worlds. Every echo is a breadcrumb, every glow a map drawn by fire. And yet the map does not tell you where the path ends. It only points to the next bend. If you have ever felt your life detonating in chapters, collapse, recovery, a breath, another shock, then you are already fluent in this language. The cosmos is not a single curtain drop. It is a stage that resets itself between acts, sometimes in minutes, sometimes in centuries, and the actors are made of the same elements that ring in your blood. That is why the astronomers gasped. That is why the control room felt like the air before a storm. Because to watch a star explode again is to remember that endings are often disguises for deeper engines, that the light you thought was a farewell may be a fuse just catching. For more content, like the video, subscribe, and tell me where you're watching from. Keep your eyes on that trembling point. The brightness is falling now as if the star were exhausted, but the furnace is already filling, the scar already knitting, and out beyond the field of view, something hungry is counting down.
The first flare had faded to an ember when the monitors caught a different kind of heartbeat, a small, hard sparkle rising from a star the size of a city, wrapped in the borrowed breath of its neighbor. Picture a furnace with its walls made of diamond-hard ash, gravity pressed so tight that a teaspoon would outweigh a mountain. That furnace is a white dwarf, the remnant core of a once ordinary star, and beside it circles a bloated companion spilling matter like a cracked cistern. You can watch the bridge between them as if it were a silver thread, a teardrop-shaped boundary called the Roche lobe, the place where gravity carves space into two unequal cups. When the companion overfills its cup, hydrogen flows across the throat of that invisible hourglass, a river of fuel guided by nothing you can touch. The dwarf does not swallow this river in a gulp. It spreads it, whisper-thin, over its surface, a skin of hydrogen as delicate as frost and as deadly as a match factory. Beneath that skin, pressure climbs. Temperature climbs. Electrons lock together into a quantum crowd that refuses to budge, a strange stiffness called degeneracy that keeps the surface from expanding and cooling when it should. Imagine inflating a balloon that will not stretch. The air has only one answer, which is heat. The layer grows denser than iron filings, hotter than a forge, until the chemistry of calm cannot hold. What happens next is not a spark so much as a contagion. A single patch ignites, and fusion runs sideways at hurricane speed, a prairie fire racing across a plain of fuel that cannot escape. You would call it a nova only because you are standing far away. Up close, it is a skin-peeling detonation, a thermonuclear flash that lifts the surface like a drumhead, hurls a gauze of gas outward, and slams the star into brilliance. The brightness can leap by factors of 10,000 to 1 million, a city suddenly rivaling a continent, and the ejected shell sprints into space at hundreds to thousands of kilometers per second. Think of paint mist from an airbrush, except each droplet is a tiny world, enriched with new elements forged in the ferocity of the burn. For a few nights the system can outshine every blue giant in its neighborhood. Then the blaze recedes, and the room seems to darken not because the universe has changed, but because your eyes now remember what power looks like. Here is the part that feels like a trick. The white dwarf survives. The blast erases the unstable film, yet spares the anvil beneath. The river resumes. Inflows continue by wind or by that slender bridge of Rochelobe overflow, and the surface begins to load again. A clock resets. The time to the next outbreak depends on a handful of levers. How fast the gas pours in, how heavy the core already is, what mix of hydrogen and helium and trace metals the donor sends across. A dwarf close to the Chandrasekhar limit, around 1.4 solar masses, is like a hillside steepened by centuries of snow. It takes only a thin new layer to avalanche, and the eruptions repeat on spans measured in years rather than centuries. You can name the repeaters like old storms etched on coastal stones. RS Afiyuki, a white dwarf feeding from a red giant's wind, its outbursts recurring often enough to be calendared, the shock of each blast slamming into the giant's shed atmosphere like surf against a rock wall. Euscorpii, a speed demon, reappearing after only a handful of years, its rise so sudden that observers stage night-long vigils to catch the lightning of its first hours. T. Pixidus, a slow drumbeat of decades, then a surprise, then another, a lesson in how nature stretches the idea of patience. Each system speaks in a dialect of light curves and spectral lines, but the grammar is shared. A thin layer accumulates, an ignition threshold is crossed, the surface detonates, the core endures, and the river keeps flowing. Look closer at what the light tells you. Balmer lines, the fingerprints of hydrogen, swell and split as if lifted by wind. Iron and helium features appear, trace witnesses to the violence of the runaway. The ejection is not uniform. Patches leave faster, like smoke drawn through a crooked chimney, and the shell develops corrugations and knots, evidence that the blast was a storm more than a breath. If the nova expands into material shed by earlier cycles, the new shock writes in radio and X-ray. Particles slung to near light speed screaming their presence, the system announcing that its past is not an archive, but a battlefield still strewn with ammunition. The glow fades, but the debris remains, a wreath of matter that will complicate every future detonation. You might be tempted to reduce this to a recipe, a dwarf, a donor, a flow rate, a threshold. Resist that urge. The universe hates recipes. Change the accretion rate by a whisper, and the recurrence time tilts. Alter the composition, more helium, fewer metals, and the ignition temperature shifts like a stove flame that now needs a longer match. Grow the dwarf a little heavier, and the layer can ignite after a thinner accumulation, the intervals shortening like breaths between sobs. Shrink it, and the system dozes for longer, until the next outburst arrives in a generation that has forgotten the last. Even the geometry matters. A red giant's wind feeds unevenly, blowing denser gusts into one hemisphere, making the runaway start in a patch that confuses the symmetry of the blast, the way a forest fire races up one slope while another remains dusted in dew. Stand with me in the imagination of scale. The layer that explodes might be thinner than a city block, yet its mass can outweigh mountains upon mountains. The flare that terrifies your detector lasted only days, yet it hurled a shell across billions of kilometers, engraving a sphere larger than a planetary system. This mismatch between thinness and power is the heart of the nova trick, the cosmos performing an industrial detonation on a sheet no thicker than a thumbnail compared to the star beneath. If you have ever watched frost lace a window pane and then vanish in an instant at sunrise, you already know what it feels like, except the sunrise is fusion and the window is gravity. Now return to the question of destiny. Each nova removes some mass, like a tax collected by the void. Each inflow adds some back, like wages from a dangerous job. If the tax is small and the wages are steady, the dwarf will grow heavier. If the tax is severe, the dwarf will be whittled grain by grain, held from catastrophe by its own eruptions. In the interim, the surroundings are being sculpted. Nested shells, wind-carved cavities, shock fronts ready to ring again. The system is writing a labyrinth for its future light to navigate, a maze of its own making. The monitors blink. Another recurrent system brightens in a different constellation, just a fraction at first, then climbing like a siren heard through rain. The spectrum sharpens, the hydrogen lines widen, velocities whisper of hundreds and then thousands of kilometers per second. And somewhere inside that glare a wafer-thin layer is being erased while the anvil beneath endures. But the light carries a new quiver, a hint that the blast has struck something waiting in the dark, and the instruments tilt as if leaning in to hear what the collision will say next. The gasp turned into calculation when the collision signatures arrived. Radio static braided with X-ray whispers, a duet only shock fronts can sing. The new blast had plowed into an older shell, a relic from an earlier heartbeat, and the impact lit invisible physics like a match dragged across sandpaper. You could see the lines thicken in the spectrum, narrow cores from slow gas overlain by broad wings from faster debris, the whole profile breathing like a lung filled too quickly. What you are watching is the star negotiating with its own past, a court where each eruption brings evidence, and the verdict is written in mass. Here is the wager the system keeps placing. The dwarf wants to grow, the universe wants to take its cut. If across many cycles, the dwarf gathers more than it sheds, its core edges closer to a weight that breaks the symmetry of calm. Astronomers give that threshold a hard name, the Chandrasekhar limit. Near 1 4/10 times the mass of the sun speak it softly, because the name is not just a number, it is a cliff. Above that weight, the lattice of degenerate electrons that props the dwarf cannot bear the squeeze. Gravity leans in with a seriousness that admits no argument, and carbon deep inside the core can ignite not as a surface fire, but as a volume-wide fever. That is the white dwarf's last word. A thermonuclear unbinding bright enough to outshine a galaxy. A Type Ia supernova written like a flare thrown across the ocean of space. But the road to that cliff is not a clean staircase. Each nova eruption can erode the very core that seeks to grow. Imagine trying to build a cathedral out of snowfall. You add a layer, the sun steals a layer. You stack a wall, a gust shears it into the street. In some systems the inflow is steady and the nova gentle, the tax small and the wages dependable, and the dwarf inches upward in mass, cycle by cycle, like a tide that cannot be turned by a handful of stones. In others the detonation bites hard, scouring more mass than the stream replaces, and the core dwindles grain by grain, protected from catastrophe by the violence that threatens it. Either way, the surroundings accumulate a history of shells, each one a fossil of a decision, and the star moves through a maze of its own making. You can watch the maze assemble. Nested bubbles expand into one another, like glass spheres set loose in a pond. Where a fresh shock catches an older thin shell, energy converts from motion into light, and the collision zone glows in radio and hard X-ray, a scar that speaks. If the environment is dense, say the donor is a red giant exhaling at a prodigious rate, the nova's blast throws a snowplow forward, sweeping up wind and amplifying the pressure until particles are hurled to near light speed. Those particles spiral in magnetic fields and whisper their presence in radio waves, the system quietly broadcasting that it is preparing its own stage. Months later, dust condenses in the wreckage, grains forged in a blast furnace and cooled by expansion, a soot that will someday blend into the raw material of planets. The light curve shows a dip as the dust veils the source, then a rebound as the shell thins, a blink that tells you chemistry is being fabricated in real time. The dwarf's mass remains the question that keeps nights long. A heavier dwarf needs less added hydrogen to trigger a runaway. Cycles tighten. A lighter dwarf must wait for a thicker coat. Cycles loosen. The accretion rate sharpens or blunts that clock. Feed the core quickly and eruptions come like drumbeats. Starve it and decades can pass between shocks. Composition matters as well. Gas richer in helium changes the ignition depth and the burn profile, sliding the threshold like a lock that now catches one tumbler higher. Even the binary dance modulates the outcome. If the orbit tightens through gravitational radiation or magnetic braking, the donor overflows more vigorously, as if a sluice gate had been lifted, and the furnace has less time to forget. You might want the universe to declare itself, to exclaim that this system will grow to catastrophe, while that one will bleed safely for ages. The sky refuses that clarity. Observations have found novae where the ejected mass is small, barely a shaving, suggesting the dwarf is quietly fattening. Others fling a shell so massive that the core must be losing ground, each outburst a diet more furious than the meal that preceded it. Between these extremes lie the stubborn cases where the plus and minus appear to balance, the system pacing a tightrope, one flare away from tipping toward escalation or restraint. The only way to know is to keep vigil, to weigh the shells, to time the cycles, to model the furnace with supercomputers that still blush at the complexity of turbulent fusion, shearing across a sphere of crystalline carbon and oxygen. For you standing under this sky, the stakes stretch beyond a single binary. Type Ia supernovae serve as mileposts across the deep. Their brightness, after careful calibration, lets us measure the swelling of the cosmos with a ruler of light. If some of those mileposts are born from dwarfs that reach the cliff by steady gain through recurrent novae, then the demographics of these repeaters seep into our map of distance and expansion, into our inference of dark energy, into how we say the universe is speeding up like a balloon inflating unevenly. If, instead, most recurrent novae whittle themselves down and seldom deliver a terminal blast, then the dominant path to a Type Ia may be a different marriage altogether, perhaps the merger of two dwarfs spiraling together like skaters locking hands on black ice. The difference is not academic. It touches the yardstick we use to size the universe. Return to the control room. The latest eruption is cooling, but it refuses to go quiet. Gamma ray detectors tick, not loudly, just enough to tell you that fresh particles are still being whipped through shocks. The radio map swells, its rim bright on one side where the shell runs into a denser patch of wind, a lopsided halo like a lantern with one panel of thicker glass. High-resolution images begin to pick out knots in the ejecta, clumps that will later cast shadows as they overrun one another, hinting that the next flare will not expand into emptiness, but into a field booby-trapped by its own history. You can almost feel the dwarf beneath this theater, compact and patient, accepting its new skin atom by atom, as implacable as a stone grinding down a riverbed. Speak with honesty. No instrument can yet weigh the core with the precision of a jeweler. We infer. We assemble clues. We count how quickly the light rises, compare it to models that relate rise time to ignition mass, and from that to the gravity of the dwarf. We measure the velocity of the shell, the ionization state of the lines, the delay before shocks turn on, and we thread these beads into a picture that is convincing enough to keep building, never tidy enough to be called settled. That uncertainty is not a gap. It is a doorway. Through it, theory and observation walk together, arguing, adjusting, returning to the sky for arbitration by a source that does not care who wins. Outside, the night has opened over a different quadrant. Another recurrent system flickers, not a copy, a cousin. Its donor is cooler, its wind gentler, its orbit wider, and yet the same arithmetic of gain and loss begins again, a ledger scribbled in fire. Somewhere between these two binaries lies the threshold that will tilt a dwarf toward a fate written in carbon and oxygen. The question now is not whether the clock is ticking, but what gear it is using, how many teeth it has left, and whether the next detonation will push the hand forward or snap the spring entirely. The instruments keep their vigil, and the dark hums with a pressure you can almost hear. The telescope swung to a place where the Milky Way spills like milk over jagged dark, and the frame filled with a wound that had grown its own wings. Two lobes of shining gas faced one another like mirrored storms, each ribbed with dust lanes, each lit from within by a source too bright for comfort. This was not a compact ember stealing fuel. This was a restless giant, a star so luminous that its own light pushed back on itself. You are looking at a life lived against a cliff called the Eddington limit, the point where outward radiance and inward gravity wrestle to a standstill, where a star's brilliance becomes a wind with fists. Imagine standing beneath a waterfall that has decided to flow upward. Radiation pressure is that reversal, photons striking atoms until atoms let go. In ordinary stars, gravity wins by a margin large enough to keep the envelope sealed. In these titans, luminous blue variables with temperatures like blue fire and luminosities that can drown a cluster, the margin narrows to a razor. A small surge in brightness puffs the surface. Opacity rises as atoms reconfigure, like shutters slamming in a storm. The envelope inflates, then accelerates outward, and mass loss becomes a flood that carries pieces of the star into space. Not a gentle solar breeze, but a gale thick with matter. A wind so dense it turns light into heat as it collides with what was shed before. Now look at the archetype. Eta Carini swells in the eyepiece like a cathedral built from explosions. In the 19th century, it staged a great eruption that rivaled faint supernovae, bright enough to be a nighttime clock in the southern sky. Yet the core endured. The outburst carved the homunculus nebula, two opposing lobes with a tight waist, a sculpture in dust and gas that expands with a discipline you can measure. Spectra from its skin carry the signature of nitrogen-rich material dredged from deep layers, proof that the star vomited part of its processed interior in that convulsion. Each lobe is not just pretty. It is a fossil of an event where radiation nearly tore the star apart and then stepped back, as if surprised by its own strength. You can feel the physics pushing from inside. Near-critical radiation pressure turns the outer layers into a boiling sea whose waves are taller than continents. Add the hand of a companion in a tight, eccentric orbit and the chaos sharpens. At closest approach, gravity from the partner raises tides through gas that is already trying to leave. Streams funnel through the inner Lagrange point. Shocks rage where winds collide head-on. Some of the escaping envelope is pinched into the bipolar shape we now see, the hourglass drawn by orbital choreography. It is not a single cause, but a crowded stage. Opacity changes, envelope inflation, binary interaction, and the sheer brutality of luminosity working together like a choir that can shatter glass. When such an eruption ignites, the light curve rises not like a cannon shot, but like a mountain growing in time-lapse. Days into months, months into years. The star becomes wrapped in its own outflow. Photons struggle through the wind and deposit energy in it, turning motion into brilliance. Astronomers call these outbursts supernova impostors, not because they are fraudulent, but because they borrow the costume of death while keeping the heart beating. Their spectra show narrow hydrogen lines that whisper of slow, dense winds rather than the broad, fast wings of true core collapse debris. Yet the luminosity can approach that of low-energy supernovae. If you stand too far away and blink at the wrong moment, you might write an obituary for a star still very much alive. The violence does not end at ejection. The new outflow crashes into older shells, and the shock converts kinetic energy into light with ruthless efficiency. The collision is a refinery that manufactures photons across the band. Ultraviolet from newly shocked gas, optical light from recombining hydrogen, infrared from dust grains forming in the cooling wake and glowing like embers under a bellows. Each former eruption becomes a minefield for the next, so that a series of pulses can string together a light curve that swells and rebrightens, a beacon that refuses to follow a simple script. Every knot in the nebula is a scar from where one wave overtook another, every filament a tear in fabric stretched to breaking. You can diagnose the engine by listening to the lines. Narrow hydrogen alpha tells you about a thick pre-existing wind. Heavier elements reveal the dredge-up of processed layers, proof that the star has been mixing its interior like a storm turning up the seafloor. In some impostors, the line wings widen with time, a hint that a faster blast is emerging from behind a slower curtain, the collision zone marching outward and announcing its advance. In others, new absorption components appear at distinct velocities like fingerprints from separate shells, as though the star were writing its own staging notes in the code of speed. Not all massive repeaters are as famous as Eta Carini. Lesser-known blue variables in nearby galaxies flare and fade, some on human timescales, others across decades, building archives that look like the heart rhythms of giants. A handful become so bright that they are catalogued as transient explosions, then level off and persist, the way a volcano can spend years in eruptive repose while slowly remaking its flanks. In crowded star-forming regions, these eruptions can be mistaken for true deaths until later spectra betray the survival of the engine. Consequences ripple outward. Dense winds enrich the local medium with heavy elements. Shocked shells spark molecule formation and dust growth, seeding the raw ingredients for future planets with material forged in the furnaces of instability. You might crave a single sentence that says why they erupt when they do. Nature offers a page of marginalia instead. Increase the luminosity slightly, through a deeper convective surge, through a burn front reshaping the core, and the envelope puffs, opacity changes, and the line between bound and unbound shifts by the thickness of a cloud. Fold in a companion, and tides lift the surface along one axis, carving a funnel where matter escapes more easily. Tilt the rotation faster, and a polar wind strengthens, carving lobes like the ones that made those mirrored storms. Each factor nudges the system toward a threshold that is less like a wall and more like a fog bank. Step into it, and you are already falling apart. For you watching this, there is a more intimate truth hidden inside the spectacle. These outbursts are the handwriting of a life that refuses a straight path. The star is not quietly swallowing fuel to a textbook cadence. It is negotiating with radiance every hour, improvising under pressures that would flatten iron. Its eruptions are not mistakes, they are safety valves and warnings, ways to shed angular momentum, ways to reshape the envelope so the core can keep burning. The light we see is the compromise glowing in public. Now the frame tightens. In the heart of the homunculus, high-energy lines flicker on and off with a period set by an unseen companion's orbit. With each periastron passage, the wind collision zone shifts and warps, changing the brightness and sculpting fresh arcs and X-ray maps like ripples from stones dropped on a lake of fire. Deeper within, the core continues its fusion story, climbing through heavier elements that cannot be shed by wind alone. The nebula expands, the shocks glow, and the instruments measure a slight shift in one lobe's expansion speed compared to the other, as if a hidden pressure were building asymmetrically. Something is gathering behind that dazzling veil, and the light that escapes already carries the tremor of a change not yet named. The alert arrived as a tremor in the timeline, a light curve that refused to behave. A star in a distant spiral brightened, eased, then climbed again, not like an echo but like a fresh decision. Spectra came back clean and stubborn. Hydrogen lines broad as storm fronts, the hallmark of a Type II event. Yet the brightness kept returning as if a hand beneath the curtain were turning a dimmer in steps. You are looking at a death that refuses to stay buried. If you have ever watched a fire find new breath in old timber, you know the feeling. An ember that was not finished with its purpose. Observers gave this apparition a name spoken like a cipher, IPTF 14HLS, and then they gave it patience. Night after night, month after month, the source pulsed with a weary grandeur, rebrightening in plateaus instead of fading cleanly into ash. Each rise arrived with the stubborn signature of hydrogen-rich ejecta, as though the star kept shedding parts of itself in episodes rather than in a single terminal cry. Archival plates whispered an even stranger clue. Decades earlier, at that same patch of sky, an earlier flash had been recorded, as if the star had coughed once before history learned how to keep watch in real time. You can call this impossible. The sky prefers the word instructive. The puzzle sharpens if you parse the light as a ledger. A true core collapse should spend most of its energy quickly, then coast through a slow decline, the cooling debris painting a predictable arc. This source drew a different map. Fresh energy arrived late, again and again, as though something at the center were feeding the blaze in installments. One school of thought pictures the remnant as a newborn magnetar, an ultradense core spinning in milliseconds and girded by a magnetic field strong enough to drag currents out of vacuum. If that engine flares, if it dumps additional energy into the expanding debris through waves or winds, the outer layers can glow anew, turning rotation into radiance the way a dynamo turns motion into electricity. The spectra, still thick with hydrogen, do not mind the origin of the shove. They simply answer by brightening. Another school follows gravity down and then back up. In a messy collapse, not all the outer layers escape. Some fall back, a rain of stellar matter tumbling toward the infant compact object. If that fallback forms a disk, it can feed the core sporadically, like a reservoir that empties through a series of irregular spillways. Each accretion episode can power a jet or a wind that slams into the earlier ejecta, converting kinetic force into light with ruthless efficiency. The late peaks in the light curve become the receipts of those collisions. The blast is not reigniting the dead star. It is lighting up the debris with fresh punches thrown from the center. Then there is the old monster of very high mass, the one that lives near a different cliff. In an oversized, hot core, gamma rays can spawn electron-positron pairs, draining pressure that was balancing gravity. The core sags, heats, and ignites oxygen in a convulsive partial explosion that ejects shells rather than throwing away the whole star. Astronomers call this the pulsational pair instability, a phrase that sounds like an orchestra tuning and then starting over with fiercer notes. Each pulse hurls a layer outward. When a later pulse arrives with a faster shell, it rams the older one, and the crash turns motion into radiance across weeks or months. The light curve no longer measures only a single explosion. It measures the choreography of shells colliding in a dark theater already filled with props. Some cases line up eerily with this script. A source cataloged years earlier staged multiple eruptions that were chalked up as luminous blue variable fits, then unleashed a brighter blast that wore the costume of a supernova for a season, only to flicker into new eruptions later as if the curtain had refused to close. Hydrogen lines stayed narrow in places, signaling dense, slow-moving circumstellar gas. Then wings broadened as faster ejecta plowed through, and the profile changed like a storm swallowing its own rain. Astronomers argued at white bards with the awkward pleasure of being forced to reconsider what they thought they knew about the way massive stars approach their last act. You do not rewrite textbooks with one light curve, but you start sharpening your pencils. To read the physics, you follow the trail of collisions. When a fast shell strikes a slower one, a shock forms, and that shock heats gas to temperatures that glow in ultraviolet and X-ray. Dust can condense in the cooling wake, changing the color of the light, dimming the source briefly as grains form, and then re-radiate in the infrared. Late-time spectra pick up narrow emission from unshocked gas farther out, marking the map of material lost before any explosive episode. Add a magnetar's breath, and you expect broad, persistent luminosity with line profiles that betray a continuous push from inside. Add fallback accretion, and you expect bumps that coincide with timescales for gas to rain back in, small plateaus like footsteps heard in a stairwell. Add pair instability pulses, and you expect distinct velocity components lined up like fingerprints from different shells, each bearing a slightly different chemical signature. What you are hearing beneath the debate is the sound of massive star endgames becoming less polite. The old picture sketched a slow march through elements until the core could no longer hold, a single catastrophic release, a fading. The new cases pencil in convulsions, outbursts in the final years that lace the surroundings with dense, structured gas. That structure matters because it sets the table for how the terminal shock will shine. When blast meets a thick ring or a clumpy wind, kinetic energy turns into light with brutal efficiency, and a faint explosion can masquerade as a bright one. Distance measurements, energy budgets, even rates of element production all depend on how much of what we see is engine and how much is collision. You standing here with your quiet breath can feel the human part of this, how discovery arrives as a crack in confidence. If a star can explode again and again without dying cleanly, what else in this diagram lives in chapters we have not mapped? Drop this in the comments. I protect my sense of wonder. That small vow matters, because wonder is what keeps the questions alive long enough for the answers to admit complexity. The sky does not mislead. It tells the truth in a language of time and light, and sometimes the grammar includes stutter and reprise. On screens tuned to radio and X-ray, IPTF14 HLS remains mostly mute, a quietness that itself speaks. Perhaps the engine is buried under too much debris for high-energy messengers to climb out. Perhaps the power source is collisions alone, clean in their conversion to optical light. In optical bands, the source sighs again, the hydrogen lines breathing with it, the velocities holding near the speeds of early epochs as if the gas has been repeatedly shocked and reheated rather than freshly accelerated. Each new uptick tempts a fresh model. Each downturn cautions restraint. Somewhere underneath that flicker, the compact core, whatever it is, keeps its counsel. A final image arrives from a different observatory. A faint, expanding arc of material at a radius that implies a shell thrown years earlier is now being overtaken by a younger, faster wave. The geometry is lopsided, brighter on one side, hinting at an asymmetric wind or a binary dance that once sculpted the stage. The next collision is imminent by every measure we trust, yet the details refuse to be predicted with the neatness we crave. The light will choose its path through a labyrinth of the star's own making, and the first sign that the crash has started may be a whisper in frequencies we are not yet listening to. The night did not get darker, it got smarter. Arrays of wide-eye cameras swept the sky in strips, subtracting tonight from last night the way you might subtract a heartbeat from the next to hear the murmur in between. Where nothing stood yesterday, a point flared today, and the software inhaled. Different images flickered like X-rays of the heavens. Constant stars canceling away, newcomers glowing as clean as fingerprints on glass. What you are watching is vigilance turned into physics. A planet-sized pulse-taking where every rise and fall of light is logged with the tenderness of a nurse at a bedside. Surveys patrol with different gaits. Some sprint, covering half the sky in the time it takes to brew coffee, trading depth for cadence so that short flares do not slip through. Others walk slowly, breathing deeply into fainter magnitudes, catching whispers that fast surveys miss. Together they build a chronicle of brightness over years and decades, a layered diary where a star's strange habits repeat like phrases in a letter written under stress. When a source brightens where it should not, the alert spills into an electronic river, and telescopes downstream pivot as if smelling rain. That first call is only the opening chord. Spectroscopes roll into position and spread the light as thin as silk. Absorption and emission features rise like mountain ranges. Hydrogen's Balmer series stepping across the visible, helium and iron and calcium stamping their signatures at precise wavelengths. In ordinary novae, early spectra can look like a city of iron, the forest of lines from singly ionized iron filling the page, then later a switch to helium and nitrogen as the excitation climbs, a transformation that whispers about temperature and density in the ejecta. Velocities etch themselves into the line shapes. Broad wings mean fast gas, narrow cores mean slow, dense winds. When a source wears a narrow hydrogen alpha crest on top of broader foundations, you can read the presence of a thick circumstellar medium waiting to be shocked. One layer from the present, one from the past, two voices arguing in the same chord. You listen in more than one color. Radio dishes turn the shock into a sound you can see, mapping shells expanding as arcs that brighten where the blast plows into thicker wind, synchrotron emission sketching the paths of electrons whipped to near light speed. X-ray instruments measure the temperature of gas heated by the shock to tens of millions of degrees, a furnace hotter than the surfaces of stars, and their light curves reveal when the shock starts biting and when it starts to starve. High-energy detectors sniff for gamma rays that sometimes rise when particles are accelerated hard enough to collide and spark. Their occasional appearance in recurrent novae is a telegram from the most violent corners of the collision, proof that these thin shells can breed cosmic rays. Infrared eyes arrive later and find dust. Grains condense in the cooling wake like frost on a windshield after a breath, dimming the optical light and then glowing in longer wavelengths. A soft ember that tells you chemistry is not just surviving the blast, it is being born inside it. Polarimeters rotate in the beam and weigh the asymmetry. Perfect spheres do not polarize, lopsided shells do. A few percent of polarized light can betray clumps, disks, or bipolar flows. The geometry revealed the way wind reveals the shape of a flag in darkness. High-resolution spectroscopy nicks each line into components, the signature of multiple shells sliding past one another, each with its own speed, each like a ring on a tree trunk formed in a different season of stress. If you catch a source within hours of ignition, you can sometimes see an ultraviolet flash from the first breakout, a candle of ionizing light racing ahead of the blast, briefly turning nearby hydrogen into a mirror before the main shock arrives to write in bolder ink. You do not rely only on the present tense. Archival mining is the art that makes the sky confess its history. Photographic plates yellowed by time are scanned and aligned so that coordinates match to fractions of an arcsecond, and a flicker from decades past can be tied to tonight's outburst as tightly as a scar to a wound. Digital archives from earlier surveys widen the window further, letting you stitch a timeline that turns a curious flare into the latest word in a long conversation. When a transient reappears at the same location years later with the same spectral style, the label repeater stops being a metaphor and becomes a dossier. Timing is a stethoscope. Recurrence intervals carry the mass of the white dwarf encoded as rhythm. Heavier dwarfs need thinner layers to ignite, so the beats quicken. Lighter dwarfs wait for thicker coats, so the beats lengthen. By modeling how fast the light rises and how hot the lines become, You infer how much fuel piled up before detonation and how brutally it burned across the surface. If the binary is edge-on, you might catch eclipses, small bites in the light curve that measure the orbit like a caliper, letting you weigh the companion and watch the period drift as mass transfer tightens the dance. Even the color evolution, the way blue drains to red and then returns, maps the cooling photosphere and the moment when the shock-powered glow takes command. Machine learning has become a night assistant with a tireless memory. Trained on thousands of transients, it can flag the odd light curve in a sea of sameness, the double rise that hints at shell collisions, the plateau that suggests ongoing power from an engine, the rapid ascent of a recurrent nova approaching ignition on a massive core. But this assistant does not replace judgment. It sharpens it, handing you a prioritized list where the weirdest candidates sit near the top like birds that do not match the field guide. Citizen telescopes join in, the balcony scopes, the backyard observatories, and their quick reactions fill gaps in cadence that big facilities sometimes leave. A nova's first night, a rebrightenings's first hour, a narrow line's first twist. Many of these have been saved by amateurs whose insistence on staying up late becomes a thread science could not do without. Even after the flare fades, the scene keeps talking. Nebular phases reveal forbidden lines of oxygen and neon, glows that only appear in thin gas where collisions are rare, telling you about the composition under the flash and whether the dwarf's core is carbon-oxygen or oxygen-neon, a difference that touches the path toward a catastrophic supernova. Late radio maps show interaction zones still bright months on, proof that the shock continues to harvest energy from the medium the system built for itself. A faint, expanding ellipse may betray a bipolar outflow sculpted by a companion's gravity, while tiny shifts in the centroid of emission hint at jets that blink on and off like Morse code in plasma. What you are holding now is a surveillance tape of the cosmos learning to repeat. Every wavelength is a witness, every instrument a translator of how energy moves from invisible pressure into visible light. Yet for all this clarity, the most stubborn questions persist behind the glow. Which systems are quietly gaining toward catastrophe, and which are carving themselves away? Which giant impostors are shedding a skin, and which are whispering that the core is near a cliff? On tonight's alert stream, a familiar coordinate has brightened by a whisper, not a shout. Too small for a press release, too exact to ignore. And the Spectrum courier is already on the road while the rest of us lean toward the screens, listening for a line to split, waiting to see whether the sky has just cleared its throat or begun another sentence. The newest light arrives like a courier with dust on its boots. A small brightening in a place where the star field used to be a flat oath of quiet. The instruments lean in, and what emerges is not just a flare but a lesson in how the universe edits itself. Each repeat explosion is more than spectacle. It is a tool that sculpts the medium between stars, hammers the rules of matter under shock, and leaves behind archives that future worlds will read as scripture. Begin with the airless ocean that fills a galaxy. The interstellar medium, thin as the breath inside a cathedral and yet heavy with potential. When a nova fireball rams that sea, it writes rings of compressed gas that curl like surf along a black beach. Those rings are not decoration, they are engines. Shocks squeeze atoms together until chemistry is forced to happen. Molecules form that could not have met in a slower world. Dust grains condense in the cooling wake, tiny stones with crystal order, seeded with carbon, silicon, magnesium, iron. Glitter that will later gather into colder clouds, then into the first pebbles of planets. If you are wearing a gold band or holding a shard of glass to the sun, you are holding testimony from furnaces like these. A repeating system does this not once but again and again, layering waves into a braided shoreline that guides where the next generation of stars will ignite. Inside each shock is a harsher classroom where particles are whipped by magnetic fields and flung into near light speed. The jargon calls them cosmic rays, but do not let the softness of that phrase blur the violence it describes. These are needles that thread galaxies, charging clouds, altering chemistry, and sometimes seeding lightning on worlds that will someday grow trees. Recurrent explosions are factories for these needles. With every collision of shell against shell, new batches are launched, and some of them carry energies that turn space into an accelerator of exquisite cruelty. You can trace their paths as radio arcs, you can catch their fingerprints as subtle heating in the gas they cross, and you can feel the implication that life in any galaxy swims in a river powered by repeaters that do not even know the word life. Now fix your gaze on distance itself, the way we measure the size and speed of the cosmos. Type Ia supernovae are lighthouses used as yardsticks. Their patterned brightness lets us read how far their light has traveled and how quickly the fabric of space is stretching, like a balloon inflating unevenly under invisible hands. But a lighthouse's reliability depends on its origin story. If some of these beacons are born from dwarfs that fatten through cycles of recurrent novae, the demographics of repeaters feed into how many lighthouses exist, which environments breed them, and how uniform their blaze truly is. If instead, most dwarfs whittle themselves down and rarely reach the cliff where carbon ignites in a runaway, then perhaps mergers dominate the census, and the yardstick must be calibrated with a different origin in mind. The stakes are not academic. They touch the claim that the universe's expansion is accelerating, a claim built on the trust we place in these distant fires. You, who are listening in the glow of a screen, might think such stakes sit beyond the reach of breath. But the same repeats that tune our cosmic rulers also tune how we read time in the lives of massive stars. Observed eruptions from luminous blue variables and supernova impostors map the final years before true collapse. Each outburst records a decision about mass loss, about angular momentum, about the shape of the envelope that will greet the terminal shock. The profile of that shock, how bright, how blue, how long, depends on whether the blast meets a clean sky or a jungle of dense shells. In a jungle, kinetic energy becomes light with a vicious efficiency, and a modest engine can masquerade as a titan. Element yields shift as well. Where the shock lingers in thick gas, nucleosynthesis proceeds under different pressures and densities, sculpting the periodic table in ways a clean explosion cannot. In that sense, a repeating star is not indecisive. It is the architect of its own obituary. There is another consequence tucked inside the light like a folded letter: dust. Astronomers used to argue that dust must be born mostly in the winds of old red stars, in the gentle breath of asymptotic giants. Repeaters complicate that picture with boldness. We watch grains appear weeks after a nova, months after a giant impostor, forming in the lee of shocks as temperatures tumble and densities sweeten. The grains are not uniform. Some are carbon-rich, some carry silicates, some bear isotopic ratios that betray high-temperature birth. Meteorites in our collections carry similar signatures, small archives of explosive chemistry embedded in stone you can hold. From this we learn that the road from star to soil is paved by cycles, not just by quiet endings. The way we catch these cycles is reshaping the craft of astronomy itself. Time domain surveys stack years of brightness like seasons in a tree. Machine learning reads those rings with a memory long enough to spot a missed beat. Amateur telescopes knit the gaps. High-energy observatories tune the treble while radio dishes keep the bass. Together they make a symphony that teaches patience. A nova's first hour matters, but so does a lopsided glow that peaks after a season. And so does a faint rebrightening years later when a newer shell ambushes an older ghost. The method has changed what counts as an event. A flare is no longer a point. It is a paragraph with clauses that arrive out of order unless you keep reading. If you need a reason beyond charts and models, take this one. Repetition is how the universe remembers. A star that erupts and survives writes continuity into a sky we thought was a theater of one-act plays. It stores energy in shells, in dust, in altered magnetic fields, in rearranged orbits. It imprints its neighborhood with structure that will influence the birth of strangers. It tells you plainly that cause and effect in the cosmos often work on the scale of lives, not moments. When you protect your curiosity, you are protecting the ability to hear those longer sentences. Tonight the latest alert is almost shy, an uptick barely wider than the noise, a spectral line that has thinned by only a breath, a radio knot that brightens on one edge, as if pushed by a hand we cannot see. The models fit until they do not. The shells line up until one of them is not where history predicted. Somewhere within that not a shock may be turning motion into light, or an engine may be exhaling through debris thick as a winter forest, or a star may be inventing a new way to postpone its end. The graph on the screen holds steady for a few minutes, a straight line like a held note, and then almost imperceptibly, it begins to rise.